Summer in Death Valley reaches 134 degrees Fahrenheit. Winter in Minnesota drops to minus 40 degrees Fahrenheit. That's a 174-degree temperature swing. Now imagine you're a steel rail, 39 feet long, trying to maintain structural integrity across those extremes. Steel expands and contracts with temperature. A single 39-foot rail section can grow or shrink by nearly half an inch. Without accommodation for this movement, the rails would buckle in summer heat or snap apart in winter cold. So engineers created gaps, tiny spaces between each rail section. But every gap creates an impact point, and every impact point creates that familiar clickety-clack rhythm. Yet somehow, modern trains travel in complete silence. How did engineers solve this 150-year-old compromise? But let's start at the beginning. The clickety-clack wasn't born from design. It was born from limitation. When railroads first emerged in the early 19th century, metallurgical technology could only produce steel rails in relatively short sections, typically 30 to 39 feet long. This wasn't a design choice. It was a manufacturing constraint. The blast furnaces and rolling mills of the 1800s simply couldn't create longer continuous pieces of steel with consistent properties. These early railroad pioneers quickly discovered a crucial problem. Steel expands when heated and contracts when cooled. A rail that fit perfectly on a cool morning would push against its neighbors by afternoon as the sun baked the metal. Similarly, rails installed during summer would develop dangerous gaps in winter. The solution was elegantly simple. Leave small, deliberate gaps between each rail section. These gaps would close up during hot weather and widen during cold periods, allowing the metal to move without damaging the track structure. Engineers called these connection points rail joints, and they became the standard worldwide. What nobody anticipated was how these practical gaps would create one of the most recognizable sounds in transportation history. As train wheels crossed each gap, they'd momentarily lose contact with the rail, then slam down onto the next section. That distinctive clickety-clack rhythm, roughly 40 times per minute at typical speeds, became the soundtrack of rail travel. What's fascinating is how this solution was independently developed and standardized across continents. Whether in the scorching Australian outback or the frozen Siberian wilderness, railroads converged on remarkably similar joint spacing. The physics of steel expansion dictated a universal solution. Despite decades of innovation, one fundamental truth never changed. Steel moves with temperature, and that movement has to go somewhere. The science behind this is precise. Steel expands at a rate of approximately 0.000065 inches per inch per degree Fahrenheit. That might sound insignificant, but multiply it across a 39-foot section during a 100-degree temperature swing, and you're dealing with nearly half an inch of movement. Those 6-millimeter gaps between rail sections weren't arbitrary. They were calculated based on the maximum expected temperature range in a given region. Engineers had to balance competing demands. Gaps large enough to prevent buckling during heat waves, but small enough to maintain structural integrity and provide a reasonably smooth ride. What's often overlooked is how these joints distribute massive loads. When a 200-ton locomotive crosses a rail joint, the force doesn't simply press down. It transfers through a complex system of joint bars, metal plates bolted to both rail ends, into the wooden or concrete ties beneath, and finally into the crushed rock ballast that forms the track bed. The clickety-clack sound itself is an engineering story. The specific frequency we hear comes from the unique combination of wheel diameter, train speed, and gap spacing. It's a sound that exists precisely at the intersection of mechanical necessity and physical limitation. Railroad engineers constantly balanced 4 competing factors: accommodating thermal movement, maintaining structural integrity, providing acceptable ride quality, and minimizing maintenance costs. For over a century, the jointed rail represented the best compromise available. So what exactly happens to a steel rail when temperature changes by 100 degrees? At the molecular level, heat energy causes the atoms in steel's crystalline structure to vibrate more vigorously. This increased vibration literally pushes the atoms farther apart, increasing the physical dimensions of the rail. It's not that the rail contains more material. The same amount of steel simply occupies more space. To put this in perspective, a continuous mile of welded rail would expand or contract by over 3 feet through a 100-degree temperature change if not restrained. That's enough movement to catastrophically buckle tracks or pull them apart at the fasteners. The seasonal stress patterns are equally fascinating. During summer heat, rails experience powerful compression forces as they try to expand. In winter cold, those same rails develop tension forces as they try to contract. These opposing forces must be managed through proper design. When expansion isn't properly accommodated, the results can be spectacular and dangerous. In extreme heat, constrained rails can suddenly buckle sideways with enough force to throw a train off the tracks, a phenomenon engineers call sun kink. These track deformations can occur with little warning and remain one of railroading's most persistent safety challenges. Modern railroads have developed sophisticated temperature monitoring systems that track rail temperature rather than just air temperature. The sun-exposed steel of a rail can reach temperatures 20 to 30 degrees higher than the surrounding air, making accurate measurement critical for safe operations. But that leads to the real question. How do you design a gap that's both precise and forgiving? The standard 6mm rail gap represents a delicate balance. Any wider would create excessive impact and noise. Any narrower wouldn't accommodate the thermal expansion in many climates. But the gap itself is only half the story. The joint bars that connect rail ends are engineering masterpieces in their own right. These steel plates are precisely shaped to match the rail profile and are secured with 4 to 6 high-strength bolts. They must be strong enough to maintain alignment while allowing subtle longitudinal movement as temperature fluctuates. The bolt pattern is carefully engineered to distribute the massive loads of passing trains. The outermost bolts are installed in slightly oval holes that permit thermal movement while still maintaining lateral alignment. This subtle detail prevents rail ends from moving sideways or vertically relative to each other. What's remarkable about joint design is how it addresses impact absorption. As a wheel crosses the gap, it momentarily loses full contact with the rail, then slams down onto the next section. The joint bars flex slightly under this impact, absorbing some of the shock that would otherwise transfer to the train and track structure. The downside becomes evident in maintenance requirements. Rail joints wear much faster than continuous rail sections. The repeated impact causes metal fatigue, bolt loosening, and accelerated deterioration of ties beneath the joints. In heavy-use corridors, maintenance crews might need to replace joint components every few years, a costly and labor-intensive process. In the 1960s, engineers asked a radical question. What if we eliminated the joints entirely? Advances in metallurgy, welding technology, and engineering understanding finally made it possible to create what's called continuous welded rail, or CWR. Instead of 39-foot sections connected by mechanical joints, railroads began installing rail sections a quarter-mile or even half-mile long. These sections would be welded together on site, creating seamless stretches that could extend for miles. Without joints, there would be no gaps, and without gaps, no clickety-clack. But eliminating joints introduced a new challenge. How do you control thermal movement in a continuous piece of steel that could be miles long? The answer lies in controlled anchoring. Rather than allowing the entire rail to expand and contract freely, engineers secure it firmly at specific points and create designated breathing zones where movement is permitted. Special rail anchors grip the rail and transfer expansion forces into the ties and ballast. The installation process is equally fascinating. Crews must lay and weld rails at a specific neutral temperature, typically around 90 degrees Fahrenheit in most North American climates. This ensures that the rail is neither fully expanded nor contracted when installed, allowing for movement in both directions as seasons change. Engineers call this the stress-neutral temperature, and it represents the optimal point for balancing seasonal forces. Install rail at too high a temperature, and winter contraction could pull it apart. Install at too low a temperature, and summer expansion could cause buckling. The financial calculation made continuous welded rail inevitable. While initial installation costs were higher, the maintenance savings proved enormous. With no joints to maintain, track crews could focus on other priorities, and overall maintenance costs dropped by up to 30%. But what happens when extreme conditions push these systems to their limits? In desert installations where rail temperatures can exceed 160 degrees Fahrenheit, engineers must get creative. Some railroads in the American Southwest paint rails white to reflect heat. Others increase the frequency of expansion zones or adjust the neutral temperature upward to accommodate the extreme heat. Arctic railways face the opposite challenge. At temperatures approaching -60 degrees Fahrenheit, Steel becomes increasingly brittle, and contractive forces can be enormous. In permafrost regions, the ground itself might shift seasonally, creating additional stress on the rail system. Special alloys and modified fastening systems help manage these extreme conditions. High-speed rail applications absolutely require continuous welded rail. At speeds exceeding 150 miles per hour, even tiny gaps would create unacceptable vibration and passenger discomfort. Japan's Shinkansen and Europe's TGV systems pioneered special welding techniques that create virtually perfect transitions between rail sections. Heavy freight presents different challenges. When a 15,000-ton coal train passes over track, the sheer weight temporarily deforms the rail, a phenomenon called rail deflection. Jointed rail handles this differently than continuous rail, with each system requiring specific design accommodations. Bridge transitions represent engineering complexity at its finest. Because bridges expand and contract at different rates than the surrounding ground, special expansion joints must be installed where tracks cross from solid ground onto a bridge structure. These sophisticated devices allow for significant movement while maintaining a smooth running surface. Every time you hear that familiar clickety-clack rhythm, you're listening to a 150-year-old engineering compromise. There's something poetic about how a sound born from technical limitation became so deeply embedded in our cultural consciousness. The rhythm of the rails has inspired countless songs, poems, and stories. It became the heartbeat of rail travel, so familiar that passengers noticed its absence when continuous welded rail began to spread. Today, that iconic soundscape is slowly disappearing. Modern passenger routes increasingly use continuous welded rail, creating a smooth, silent ride that would astonish 19th century travelers. The clickety-clack is becoming a rarity, preserved mainly on heritage railways and rural lines. What's most elegant about railroad engineering is how it balances competing demands. Temperature variation, structural requirements, passenger comfort, and economic reality all push in different directions. The solutions, whether jointed rail or continuous welded rail, represent careful compromises that respect the immutable laws of physics. Despite all our technological advancement, those fundamental principles remain constant. Steel still expands and contracts. Forces still need to go somewhere. The engineering challenge isn't to overcome these realities, but to work harmoniously with them. Perhaps most fascinating is how we've romanticized what was essentially an engineering limitation. That rhythmic clickety-clack wasn't designed. It was an acoustic side effect that became synonymous with the romance of rail travel. We adapted to it, found comfort in it, and eventually missed it when technology rendered it obsolete. And now I'm curious. Have you ever wondered why some trains can brake from 200 miles per hour to a complete stop in less than a mile? The physics of stopping these massive vehicles involves equally fascinating engineering challenges that balance safety, physics, and mechanical ingenuity.